Okay, so we're going to be talking about limits at infinity as well as, infinite limits. Sort of a 2-for-1. An infinite limit is pretty straightforward. It's something we've already talked about, but we're just going to now officially allow you to utilize this terminology. Let's say that you've got some function, and at 3, there's an asymptote. A rational function y equals f of x. Say what is the limit of f of x as x approaches 3 from the left. Up until now, we've said what, class? What is the limit of the function as x approaches 3 from the left? And we haven't said, yeah, it does approach positive infinity, but that's not what we've said. We've said does not exist. Reason, unbounded behavior. Okay, well now, basically, if you want to put infinity, that's fine. So we see that it continues along unbounded. There are some issues with putting infinity here because technically the limit statement says I need a number over here, and infinity is not a number, it's a concept. But we all know what we're talking about. And the same thing if you say the limit of f of x as x approaches 3 from the right. Keep going, Rigel. What would that be? Negative infinity. Approach 3. You see that the function approaches negative infinity. Technically, it's unbounded, but we would say, and so therefore the limit doesn't exist. But this communicates that idea. It doesn't exist. It's unbounded, decreasing forever. That also helps us know that there's an asymptote right there. So a question is, where do these things occur? What do those look like in a function rule? Not where, but we can say, what do asymptotes look like in equation form? Anybody want to venture a guess? James, what kind of thing could lead to an asymptote like that? It's not a sine function, right? Gracie, any idea? What type of, if I had, f of x equals, what would this part over here look like that might lead to one of those things? It leads to, at least to an asymptote.
Like a fraction. X minus something with x in the denominator.
Yeah, exactly. And that is, it looks in the form where you've got a rational function, something divided by something else, and you have some limitations because you don't want to have zero in the denominator. In this case, you would have to have something, I don't know what, over x minus 3. Because when x does equal 3, then you end up with 0 in the denominator. So it looks like this. It looks like some sort of situation where you have a 0 in the denominator. That's the answer. Something that would lead to 0 in the denominator. This is called a non-removable discontinuity. of non-removable discontinuity. Now that may make you wonder, is there such thing as a removable discontinuity? And the answer is yes. A removable discontinuity would be something like this. Answer, yes. Right there. Removable discontinuity would be here in this function at x equals 2 because we can see the limit does exist there, correct? Does the function exist at x equals 2? Harley, what do you think? Does the function exist right here? No, it doesn't, because there's a hole and there's no other dot anywhere else. But does the limit exist? Yes. The limit is approaching the same number from the left and from the right. So you might say, what does this look like as a function? Well, let me tell you. It looks like this. F of x equals x squared plus 2x minus 8 divided by x squared minus 4. So let's see. What is the limit of this function? X squared plus 2x minus 8 over x squared minus 4 as x approaches 2. James, what's going to happen if we do direct substitution on this?
Going to get a 0 on the bottom.
You're going to get 0 in the denominator, right? So you might say, oh, 0 in the denominator, I would expect that's going to be an asymptote, right? That's what you just told me a second ago. 0 in the denominator should give an asymptote. And not necessarily. A 0 in the denominator could be an asymptote or it could be a whole. It depends on whether or not you can do that trick that we did last week, namely the factor method. So let's see if we can factor this quadratic polynomial here. X squared plus 2x minus 8 into two terms. Let's see, these other terms must multiply equal negative 8 and combine to form 2, so that looks like a positive 4 and a negative 2. We see x squared minus 4, and immediately our mind says, oh, I know that's the difference of two squares. That's x plus 2, and that's x minus 2. This right here is a great example because you can see once it's factored, what are the two situations that are going to give you 0 in the denominator? X equals negative 2 and x equals positive 2. If you visualize, plug in negative 2, you get 0 right here. If you plug in positive 2, you get 0 over here. However, in the numerator, we also have an x minus 2. So those parts cancel, and we end up with x plus 4 over x plus 2. And we say, what's the limit of that? I can do direct substitution right now. That's going to be 6 over 4. So that's 3 halves, 1.5. So a removable discontinuity is still a discontinuity. It's a place where if you're drawing that, drawing this with your pencil or pen, you would have to lift your pen up and then continue on. So it's a discontinuity. However, it's removable in the sense that we can still evaluate the limit there at that statement. The limit of that function as x approaches 2 is exactly 1.5. However, the limit of f of x as x approaches negative 2 would be what, Harley? What's the limit of f of x as x approaches negative 2 on that graph?
So, will we plug it back into that one?
You could. Unfortunately, if you plug in negative 2, you get negative, you get some number in the numerator, but who cares? But here, look at the denominator. You get 0 in the denominator. Okay? Well, yes, but not explicitly just for that reason. Look at the graph and tell me what is the graph approaching as x approaches negative 2? Infinity from the right and negative infinity from the left. So we've got unbounded and behavior differs from left and right. Okay, so that does not exist. The reason why I said if you just plug it in, you get does not exist. If you were to plug, so at x equals negative 2, we have a non-removable discontinuity. You can't pull it out. You can't factor. Nothing's going on. At x equals 2, you have a removable discontinuity because you can do the factoring and cancel some of those things out. Now, what I want you to see though, if you had tried direct substitution here, you would get 2 squared, which is 4, plus 4, minus 8, all over 4 minus 4. So you get 0 over 0. If we had just plugged in 2 with the direct substitution, we get 0 over 0, which does not exist. Okay? And you might say, oh, the limit doesn't exist there because I did direct substitution and therefore it doesn't exist. And we found out last week that that is not the case. Just because you try direct substitution and it doesn't work does not mean that the limit doesn't exist. It just means that there's a hole in the graph. Okay? Direct substitution is great when it's a well-behaved function. But if you have like a rational function like this where you have stuff in the denominator, direct substitution doesn't always work. It will give you, direct substitution gives you a does not exist answer when in fact there is a limit. The limit is 1.5. Okay? So that's the difference between a removable discontinuity and a non-removable discontinuity. A removable discontinuity, you can factor, you can do some sort of mechanism like the thing that we just graded, and you can actually come up with a limit. And it tends to look like a hole. A non-removable discontinuity looks like an asymptote. And no matter how much you factor and how much other stuff you do, you cannot simplify it and end up with an actual number. There's no way we're going to find an actual limit on that. Okay, any questions? Okay, so that's infinite limits. Next up, limits at infinity. We talked a little bit about this during pre-cal, so it shouldn't come as too much of a surprise. So I want you to consider two situations. Situation in which a function in which the numerator grows faster than the denominator, and a situation in which the denominator grows faster than the numerator. Okay? So consider x squared over x cubed as x approaches positive infinity. And also consider the limit as x approaches infinity of x cubed over x squared. So James, which one of these is going to grow faster? The x squared or the x cubed?
X cubed.
The x cubed, okay? So in this first problem right here, what we're looking at, 1 squared over 1 cubed, so that's like 1 over 1. 2 squared over 2 cubed, so 4 over 8. 3 squared over 3 cubed, so that's 3 over 27. Okay? Well, this is 1. This is 0.5. So with the calculator real quick, what's 3 divided by 27? 0.1111. Okay? What, just based on this trend right here, what appears to be happening to this ratio? It gets smaller. In fact, that's true every time. If you have the denominator getting larger and larger and larger, and it's getting larger faster than the numerator, then you're going to end up approaching 0. If we were to go one more, we could go, let's just skip 5. So 25 divided by 125. Say it again? 25 divided by 125? 0.2. This doesn't seem to be correct. I said 3 over 27. I should have said 9 over 27 because it's 3 squared. So I think that was 0.22. 0.32. Okay. Not thinking clearly. There we go. All right, but okay, so that matches a little closer. So it's approaching 0. So if the denominator grows faster, your ratio approaches 0. What about if the numerator goes faster? Let's see. Well, it would just be the reciprocal of these things. So 1 over 1, 8 over 4, 27 over 9, 125 over 25. That's 1, that's 2, that's 3, that's 5. Right? So if that numerator is growing faster, then the ratio, as x approaches infinity, is going to get larger and larger and larger. It's going to approach infinity. So then you can say, all right, what about this situation? If I have x to the 5th plus x cubed plus x squared plus x over x to the 4th plus x squared plus x. The numerator being larger, okay? Now, you might say, well, I don't know, what about all this stuff? What does that do? And the answer is, who cares? Because what if I were just to compare that x to the 5th versus the x cubed? This one's going to be going faster than this one. In fact, out of all of those terms, the one with the highest exponent is going to be the dominant number in that numerator. Okay? That's good. You know, by the time we get to 100 billion, million, trillion, this guy is going to dwarf whatever those are. So you don't even really need to pay attention to those other terms. And the same thing right here, you don't even need to pay attention in the denominator to those lesser terms. We really just want to look at the exponent in the numerator, the largest exponent, okay? And then we want to look at the largest exponent term in the denominator. And that simplifies it greatly because now I can see this is a situation where the numerator is growing faster than the denominator. Therefore, I'm looking at infinity. Look at this problem. The limit of 3x squared plus x over 5x to the 4th minus 100x. Still, same sort of situation. I'm going to look at the term up here in the numerator that has the highest exponent. So this guy over here with the x, I don't even care. In the denominator, this one has a minus 100x. Who cares? It doesn't matter. I'm looking at the x to the 4th. Okay? And so in this situation, I have an x, even though there's a 5x fourth, I mean, this one could be, I could have 13x squared. And you might say, that coefficient's bigger than this number. Yeah, it doesn't matter. As x approaches infinity, the multiplier here, x squared, I mean, we're going to get 100 squared, 100 times 100 times 13, versus 100 times 100 times 100 times 100 times 5. That x squared is really what's going to matter. That's what's going to drive all of this. So we have an x squared versus an x to the fourth. An x to the fourth is larger. When the denominator is bigger, you can almost think like it swallows it up. So all that to say, those coefficients really don't play a part. Okay, we're primarily looking at the exponents and looking at the highest present exponent. Now, that leads us to the question, what if they tie? Right? What if we have the limit as x approaches infinity of 7x to the fifth minus 2x over 8x to the fifth plus 14x.
Isn't it just a fraction of the two, the highest?
It is. It's the ratio of the leading coefficients. So if they tie, we can think of, well, essentially, in the numerator, that minus 2x squared, that doesn't even matter. And in the denominator, that plus 14x, once again, that really doesn't matter. So we're really just looking at a 7x to the fifth over an 8x to the fifth situation. And as x gets larger and larger and larger and larger, well, this one is going to be 7 times the x to the fifth, and this one's going to be 8 times the x to the fifth. And essentially, you have an x to the fifth in the numerator, and x to the fifth in the denominator, and they would like cancel each other out. And your answer is going to be 7/8. The coefficient here divided by the coefficient there.
There's no code. I mean, if there's no numbers in front, it's just gonna be one.
That's correct. Because technically, if there is no numbers, then there is a number, and that number's 1. We're recording, right? So if I were to write this down like it sort of want to have a summary statement, the limit as x approaches infinity of f of x over g of x, we could say if f of x, or, well, hold on. I guess we'd say if f of x grows faster, then your limit is going to be approaching infinity. If g of x grows faster, then you're approaching 0. If they tie, then it's the ratio of the leading coefficients. Leading coefficient is means the multiplier in front of the term that has the highest exponent. All right. Now, one question is, what does this look like on a graph? Well, a situation where x approaches infinity might be something kind of like, oh, you might have an asymptote over here. But if if f of x approaches infinity, that means you're going to have something where its function is increasing without bound. If you have a situation where the function approaches 0, that means that as x gets larger and larger and larger, your y values are getting closer and closer to 0. So it could look something like this. And if you've got a tie where you get the ratio of leading coefficients, that means that your limit is or your function is approaching a specific number. So in our problem up there, where our function was approaching 7/8, that's going to correspond to a horizontal asymptote at that number. So, third situation where it's a tie, that's a horizontal asymptote at that particular limit. If the denominator grows faster and you approach 0, you also have a horizontal asymptote, but it's at y equals 0. And this one, if it approaches infinity, that just means that it increases, the function increases without bound. So there's one more part of this I want to share with y'all, but does anybody have a question about this? James? Gracie? Harley? Bradgel? Should be able to get to some problems here in about 5 minutes. Okay. The only other thing is that I want to tell you, sort of a warning, watch out for negatives. Just as a reminder, a positive over a positive equals a positive. A negative over a negative equals a positive. A positive over a negative equals a negative, and a negative over a positive equals a negative. Okay? Also, if you take a positive number and square it, what type of number do you get? Positive. A negative number and you square it, what type of number do you get? Positive. A positive number and you cube it? Positive. A negative number and you cube it? Negative. In fact, if you take a positive number to anything, I'll put any, of course it's going to be positive. If you take a negative number to an even power, it will be positive. But if you take a negative number to an odd power, like cubed, or to the 5th, or to the 7th, then it will be negative. So for instance, look at this one. The limit of negative 3x to the 5th plus 10 over 4x squared minus 7 as x approaches infinity. First question is, who's going to win, numerator or denominator? Say again? Numerator. Okay. Well, according to what Mr. Goddard told us, and we figured out earlier, if the numerator grows faster, it's approaching infinity. So I don't even have to think, it's just infinity. And if you put that, then you're not thinking, because you gotta check yourself. Watch for the negatives. Yeah, it's approaching infinity, but look at this. It's -3 times essentially infinity. Okay? And so you're always gonna, this numerator up here is always going to be negative. So therefore, we put negative right there. So this actually approaches negative infinity. Now, it would be different. What if it was as x well, I'll just do my pre-planned examples here. This is the limit as x approaches negative infinity of 2x cubed minus 9 over x squared. First question you have to ask, who's going to win, numerator or denominator? Numerator, because we've got an x cubed, okay? Now the question is, we know it's going to be infinity because the numerator wins. The question is it a positive or negative infinity? And I've got some interesting stuff going on here. We have negative infinity, and so when I multiply it in the numerator here, it's going to be raised to an odd power. So it's going to be a negative times a negative times a negative, which gives me negative in the numerator. My denominator is a negative squared. So negative times negative, which is going to give me a positive. So a negative over a positive is going to give me a negative. If instead of that we had the limit as x approaches negative infinity of 2x to the 5th over x cubed, numerator still wins, right? Because it's x to the 5th versus x cubed. However, we've got negative infinity to the 5th. So negative, 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 okay, who cares? It's an odd number. Odd numbers negative, it's going to be negative right there. X cubed is going to be negative. Okay? Negative over negative is a positive. So it's positive infinity. There's a few other variations here, but y'all get the idea. Okay? So just keep your wits about you. If you do have an infinity, check the signs, positive, minus, see, plug it in. It shouldn't be too difficult. And if you have a question, you can always ask. We have 5 minutes left. Let's go ahead and scan through this, see if there's some problems I can help you with before I let you go. Yes. Try to post that one in together sometime. Alright, so let's look at that one. I think I know. These first couple aren't too bad. I've got the graph there for you. The limit of this function as x approaches 3 from the right. What do you think there? Infinity, yeah. That's not too bad. These graph ones, I think you can handle no problem, right?
On 3, since it doesn't actually give us, are we just assuming that the asymptote is at pi over 3?
Yes, the function of tangent x does have a, well?
Because isn't the asymptote at pi over 2?
Ooh, good question. So is this a distractor problem? Yeah, the asymptote's right there, negative pi over 2. So negative pi over 3, you should be able to just plug that in. Did y'all catch that? On number 3, the asymptote's at negative pi over 2 and at positive pi over 2 and at negative pi over 3 is like right here. I mean, that's like negative 1 pi, and this is negative a half. Negative pi over 3 is somewhere like down here. And there's not an asymptote there. You should just be able to plug in. You should be able to plug that one in. Now contrast that with cotangent over here. As x approaches 0, notice at 0 there definitely is an asymptote. So Raj, what would you say for number 4? Not sure? The limit, well, you got the graph here, okay? As x approaches 0 from the positive. Negative infinity? Yeah, I agree. So just lots of graphs there. You can. What about? Let's skip on to another page. Maybe number 9. The limit of 3x times cosine of 1 over x as x approaches infinity. So that means as x approaches infinity, that means we go this farther and farther and farther this way. James, what does it look like that graph is doing as x is approaching infinity?
Increasing.
It looks like it's increasing, is that what you said? Yeah. It looks like this just keeps going up and up and up, with no end in sight. Conclusion, the limit here would be? Infinity. All right, what about number 10 though? This says the limit of e to the negative 2x minus 2 as x approaches negative infinity. What does it look like it's going on there? You think it's going up here and going to go up this way? Do you think it's just kind of flattening out? It does kind of look like it's flattening out. So what, maybe negative 2? Okay. I'll let you eyeball that one. If you wanted to be sure, what you could do is you could plug in some values. You could plug in like negative 10 and see where it is, and then plug in like negative 100, and then plug in like negative 1,000, and you could plug it in here into like your table and see what it would give. Does that make sense? So that'd be fine. And then here at the very end, we've got some of those problems that we were working on.
On number 12, would you call that infinity? Because it's continuing to go up? Or, because I feel like it's going back down, yeah.
It will.
Or would that just not exist since it's oscillating?
This is an oscillating function. It goes up and then it goes down, and then it goes up and then it goes down.
So it do not exist?
Yeah, it seems like that it's approaching positive infinity, then it approaches negative infinity, then it approaches positive infinity. Yeah. All right. So today we talked about limits at infinity and infinite limits. This is one of those rare exceptions. Get this done tonight so that we can grade it tomorrow, so we'll be totally ready for the review tomorrow. Okay. When it comes to that memorization quiz, I'll give you probably 10 minutes, just because you don't need more than 10 minutes on that. All right, I'll see you tomorrow. James, go and turn it off there.